All right, howdy everyone. We're continuing our lecture on vision, topic 2, and this subsection is on the importance of contrast. How do you measure contrast? How do you quantify it? Why is it important for making visual imagery? And also text. So what makes text readable with regard to how our visual processing system works? All right, so first of all, we'll define contrast as the mathematically measured difference in what we call luminance. Luminance is a physical property. It's basically saying how much light energy is coming off of this object or being emitted from this display, for example. And it's the difference in that light energy between the lightest areas of the object you're seeing and the darkest areas of what you're seeing. Or sometimes they say between the foreground, the thing you're supposed to identify and distinguish, and the background, that which you're trying to ignore. So the difference between those two will give you basically a quantity that helps understand how easy it can be processed or how difficult it is to visually process. So it's expressed as a ratio between the difference and the sum of the two. So the lightest and the darkest areas in this screen right now that are emitting light into that your retina is picking up, the lightest and the darkest, so even the black text here, is emitted light. It's very low intensity. The white, the aspects of this image are considerably higher intensity or higher luminance. But the black also emits some amount of light energy. So we want to consider that. And so we sum the two of them. If it's, at least if we're talking about imagery versus text, would be the foreground is the text, the background is the not text. But we take the difference between those two, which should be in most cases a positive number, but not necessarily. This could be negative. And then the sum of the two. And so if you have a higher magnitude here, so it could be negative, but high in, the magnitude is large. That means there's a greater difference between the light and the dark, and ultimately higher contrast and better for your visual system to process. Black on white is a larger difference in luminance than black on gray. So black on white, if we put into this equation, is going to give us a larger value than black on gray. And so here's a little bit. Oh yeah, in another. All right, one more slide. Again, I mentioned you could have negative or positive numbers here. So negative contrast comes from the fact that the foreground, which is the black text, has a lower luminance level than the background, which is the white area here. So the white area being a higher value, and if you take the foreground minus the background, now you're going to have a negative number, okay? And so that's how we get a negative contrast. If you reverse those two, you have a lighter foreground and a darker background, you're going to have a positive value. So this is positive contrast. You can also have color contrast, and this is a good example of what I talked about with in the color vision 2.3 topic, of something that's offensive to the eye and is potentially a bad idea. Although you can have foreground and background, different colors. The important thing for measuring how clear is this, though, is the difference in the luminance. So it might be that this is hard to distinguish from the background, even though the colors are different, the hue is different. Maybe if the luminance is very similar, it's that much harder, to be able to process it. All right, so let's do some math here. So let's go ahead and just assign values and say the white background on this screen has a luminance value of 10, and the black text has a luminance value of 1. Let's say dark blue text, it's not as dark as black. It has a luminance of 3. And as we get lighter here, light blue, let's call that a luminance of 7. So how do each of these, calculate in terms of contrast against the white background? So we plug them into these equations here. We see for black text about 0.82, for dark blue about 0.54, for light blue about 0.18. The larger this number, the clearer, the better for your visual system to process, especially if we're talking about text. So it gets harder and harder to see this light text on a light background. Similarly, dark text on a dark background would be a low contrast and difficult to see. We can also combine, you don't not just white background. So I know that the luminance of this blue is 3 and the luminance of this is 7. I can put those values in and determine the contrast of this as well. Okay, now in addition to contrast, the spacing of text, the shape of text and how they're spaced matters in terms of the agreeableness and how well people process verbal, letter semantic based visual items. So what they say is 3 cycles per degree. So if you have a degree of visual angle and say we've got roughly 3 things that you might need to see within that degree, this is going to be the maximal visual sort of definition. I can't, if this is, I don't quite know how to rectify it with this minutes of arc. So I'll just say that this is, again, something that comes from the textbook and I can't fully explain it. So I don't, but it is in the textbook. So 3 cycles per degree, that is a standard. I still think you're going to want to do more with acuity, and maybe I'll figure it out and I'll post an addendum here. Black on white is the most readable. White on black, like this, is conceivably the same contrast and so should be equivalently readable. The issue with this, or what they find, is that it actually doesn't turn out to be as nice on your eyes in terms of the clarity of what you're processing, because I looked this up once. See, I don't think I have it on the text. I do. So glare factors are going to be an issue. So old-timey computers used to have, this would be their black would be their background, and there would be the foreground would be brighter, either white or green or some other color, mostly to do with the fact that it costs a lot less energy to project white things on a mostly black background than vice versa, right? So with the screen in front of you right now, there's a lot of light energy being produced for just background. And while that makes for a nice viewing experience, it's not great for power consumption, I guess. Other factors, if you have it in this mode, glare is going to be more of an issue. The light reflecting off of this screen is going to obscure the important aspects of this, which are the white letterings. We'll talk more about glare in topic 3, illumination. And our pupil diameter is going to be slightly larger, slightly dilated in this case, because it needs to let in more light for a relatively darker emitted display surface. So as that pupil diameter dilates, it also makes it a little bit harder for us to resolve detail. So the way that, the larger your pupils are, the more possible light distortion that happens when light passes through the eye. It's like having a camera with a long-term exposure, and there's more noise that comes in that way. So black on white is most readable. Black on red is very bad. All right, here we go. And I do have a question I like to ask on things that requires you to think about this and to think, why in low lighting would, if I have, let's say this is red paper and I print with black ink on red paper, think about this. Why in low lighting would that be especially bad? And take a minute, think about that. I'll give you a hint. The Purkinje shift factors in here, the relative sensitivity of rods and cones to particular hues of light, and likely in low lighting, which cells, which receptor cells, rods or cones, are going to be more dominant in your visual experience. And if you're confused, I would say go on back to probably section 2.2 and 2.3, where we talk about color and trichromacy. But the answer here, in low lighting, remember our rods become the more dominant In fact, our vision can eventually entirely be from the rods. The cones are not active at all. And the cones are what we need to see reds. Remember, that end of the spectrum is only processed by our cones. If our cones are not active, we only have rods going. Rods are insensitive to the red end of the spectrum, the far red end. And so what happens, this red background is to our eye the same as that infrared flashing TV remote would be to our eye. It's insensitive. It has no experience of emitted light. It doesn't sense it. So it would be like if it was a red paper and black ink on red paper, then in low light conditions, when like scotopic vision, when only my rods are active, it will look like black on black. So there you go. All right. Okay, so also shapes matter, right? So for making text readable, familiar fonts are important. Some of you may have a very strong opinion about things like serif fonts, like do they have the little curlies on the ends, or non-serif. I think this is non-serif font, and I forget which people like and which people don't like, because I forget, but this is an easier one to read. Block letters might look cool, a little harder to read quickly. Other non-standardized shapes, they look cool. They don't help a human process verbal information as well as straightforward familiar fonts. The case matters. So there are design factors we'll talk about with documentation and the design of warnings. This capital WAR, this warning all capitalized, is a great use of all caps. It's a single word. It's designed to capture attention, and it's designed to convey severity. Of course, if we talk with caps lock on, all of that ability to distinguish I'm really trying to capture your attention from this is detail gets lost. So caps lock works if you're trying to attract attention. It doesn't work for people to keep their attention on your message. So if you write a whole bunch of stuff in all uppercase, you have a harder time getting people to process the whole thing. So when you want to capture attention, use shorter phrases or single words and all caps. For isolated, single words, uppercase. And for more description, use mixed case. Mixed case is more familiar, more friendlier for the human reading visual system. And this is potentially one of the reasons why, is when you have mixed case, you have additional cues that your visual system can use in identifying shapes and words. So if I see a word that is blurred out but shaped about like this, I get more information than it. So that can be the word the. I hope you see how this is, the height of the different letters here. That's going to encode more information that helps me differentiate what is this word than if they were in all caps. If they were in all caps and all the same size, I don't have this benefit here. And so then, what does this say as we blur this out? We can use clues like the height, the relative height of the letters, and the context for, well, what are words that have about that shape pattern? We see this word and this word all the time. And so these shape patterns start to be familiar to us, even if it's not explicit. So these are all clues that help us, visually identify text. Okay, that's it for this topic. I think we got one more to go.